So in the candle lab, we burned a candle. In this case, it's paraffin, which is a hydrocarbon C25H52. And kind of side notes, all hydrocarbons, so hydro is hydrogen, carbon is just carbon, so hydrocarbons is a long chain of carbons and hydrogen. So I'm going to draw one. I'm going to draw propane. Carbon wants to be bonded to 4 things total. Since it's already bonded to carbon, this one could bond to 3 hydrogens. The middle one can only bind to 2 hydrogens, and this end can bind to 3. If we have butane, if we have butane, which is 4 carbons, the middle carbons can only bond to 2 H's, and the end carbons can always bond to 3. So this pattern is always the same for hydrocarbons. So the ends can bond to 3 hydrogens, the middle can bond to 2. So all hydrocarbons have the same empirical formula, which is C to N, which is the amount of carbons. The hydrogens are going to be 2 times the number of carbons plus 2, because the ends will have 3 instead of 2. So this is true for all hydrocarbons. If you look here, C25 times 2 plus 2. Propane is C3H. 2 times 3 is 6, plus 2 is 8, and we count 1, 2, 3, 4, 5, 6, 7, 8. This is C4, so 2 times 4 gives me 8 plus 2, which is 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is true for all hydrocarbons, no matter how long it is. Eventually, hydrocarbons will be stable if you get too long, but it works in all cases. So we want to find out in the candle lab, back to this one, how much energy this has if we burn it. So when we're burning it, remember it's combustion, we're going to consume oxygen, or we need oxygen. We're going to produce water and carbon dioxide. And we want to know how much energy, or delta H, is going to produce in that fire. It's going to produce heat. Once we get it going, it's going to have fire, and we need some way to measure it. So the best way to measure it is using something that we've done before. So we are going to go, okay, well, we're going to set up some sort of apparatus. I'm going to have a can, and I'm going to put some water in it. And this water, I'm going to go know my initial temperature, and I'm going to measure my final temperature. And what I'm going to do is, whatever this fire did, here's the wick, here's the fire, however this fire was able to heat up this is the amount of fuel that I consumed. So that's kind of our lab. We're going to measure the initial temperature, the final temperature, and then we're going to mass this one and mass this one. We won't find the M for both of these because we need this for the delta Q, or sorry, delta H, MC delta T. And then we need to know this is how much we consumed. We know the balance equation, but this is in moles, right? 1 mole of C25H52 will give me, let's balance the equation, C25 here, 52, so that means I need 26 here. And then 25 times 2 is 50 plus 76, or sorry, 26 is 76, so 50, oh, what's going on? 50 plus 26 divided by 2 will give me 38. So here is my balanced equation, but I want to know this stuff. So in our lab, we got these following data points as we watch Mr. Bender do it. And I'm going to just write down one of them, kind of just to go through it, since all 4 of them are going to be the same kind of information. I don't want to be redundant. So we measured the graduated cylinder, which had a mass of 44.45 grams. We measured the graduated cylinder plus the water. So we added some water, about 107.90 grams. Then we had the mass of the candle, because we want to know the before and after. So that was 39.87. And then we're going to measure the initial temperature. And that was 4.0 degrees Celsius. And then we're going to measure the final temperature. which was about 42 degrees Celsius. And then we're going to mass the candle again, which was 39.53 grams. So in our lab, this is what we measured, or at least wrote down. And now we want to find out this delta H. So let's do it. All right, so the first thing is we don't know how to measure this directly, so we're going to measure it indirectly. Remember, this candle is going to heat up this water, so I want to know how much energy was gained by the water. So its mass was these two subtracted, so I'm going to have 107 minus 44.45, so 107.9 subtracted by 44.45, and I get 63.45 grams. The delta C, or sorry, the C specificity of water is 1 calorie per gram degree Celsius. And the change in temperature, it went from 4 to 42. So final, 42.0 minus initial, 4.0. And I'm going to subtract those two. 40, oh, it's 38. But anyway, now I'm going to multiply across. So clear 38 times 63.45. And I get a delta H of 2411.1 calories. And I believe this is little c. All right. Now let me just make sure my sig figs are right. Technically, this is my smallest sig fig, so let's just round it off to 2400 calories. All right. So this is burned, but it's not like a mole. We didn't burn a mole of this. We didn't even burn like the whole candle. But we did burn a certain amount, so we want to find the mass of the candle. So the mass of the candle is final, or initial minus final, because we want to know this is the amount it started with. We burned some away, so we're left with this one. And if we subtract the 2, 39.87 subtracted by 39.53. So we consumed, technically if I did final minus, let me do that. Let me do final minus initial because that's how we normally do it. So final, 39.53 grams minus initial 39.87 grams is going to give me negative 0.34. So I'm losing this much fuel, so I used it up. Now, this much fuel made that many calories. So if I wanted the unit calories per gram, that's all I'm going to do. Just divide it. So 2400 calories divided by 0.34 grams. Because I just want to know a ratio. So that's why I really don't care about the sign. I know we're losing a mass, but I just want to know a ratio. So if I divide those two, 2400 divided by 0.34, I get 7,058, so I'm just round it off to 7600 calories per gram. Let me actually keep my original answer, so see if I'll get more accurate. So 24.1.1 divided by 0.34, and I get, yeah, oh, what? What did I do wrong? 2400 divided by 0.34. Can't be that much difference. 2411.1. What? Okay. 2400. Oh, it does make that much difference. All right, I'm going to keep my original one because it makes a huge difference. So it's good practice to only round at the end. 0.34. I just can't believe it was that much of a difference. So 7091.47. I'm going to round to 2 sig figs, so 7100. So wow, it does make a huge difference. So yeah, it's always better practice to round at the end. I didn't think it'll be 500 calories difference, but it is. All right, so this is what it is, 7,100 calories per gram. And we're able to figure it out. Once we have there, ask for percent yield, meaning how much of the energy was actually collected, even though we know the given. The given is 10,000. So if we divide the two, we get 0.71 or 71%. So we were 71% efficient in collecting the energy. Some of it did dissipate into the environment, so the can didn't go all there. We could have there's soot on the bottom, so it's incomplete burning. And also, the water could radiate temperature out. Since it's getting higher, as it's getting hotter, some of the heat could escape into the environment. So if we really, really wanted a really accurate answer, this should be an enclosed system. But it's not. So this is as good as it gets for us. All right, so hopefully that makes sense. This is the candle lab that we did in class.